In this video, we're going to talk about how to simplify radical expressions. I want to talk to you about this new notation here. You're going to see us use a radical. And so let's talk about what the different parts of the radical are called. Okay, so as you know, this is the radical symbol here. You've got this radical sign. You will often find a little number tucked in here into the radical sign, and we call that number the index. Now, if you see a radical without a little number then we say that the index is 2, and you'd be talking about a square root. If there's a little 3 in there as an index, then we would be talking about a cube root. And if there's a little 4, then we would be talking about a fourth root and so on. So that number is called the index. And the number that's inside the radical that we're taking the root of, that's called the radicand. Okay, so for example, here in example number 1, we are looking for the square root of 64. So 64 is called the radicand, and then n is 2, the index when it's not written in. That's understood to be 2, and that means that we're looking for a square root. So what does this represent? Well, when we're looking for a square root of 64, we're looking for what number do we square to get 64? What number times itself equals 64? That's what square root of 64 means. And so you know that number to be 8, right? Because 8 times 8 equals 64. So 8 times itself equals 64. So we say 8 is a square root of 64. Okay, in problem number 2, we're looking for the square root of negative 121. So what number times itself will give you a negative 121? Now, some of you may be thinking, well, I know 11 times 11 is 121, right? 11 times 11 is 121. But our radicand is negative, so we can't say that the square root of negative 121 is 11. What about negative 11? Well, negative 11 times negative 11 would still give us a positive 121. So is there any way that we're going to be able to multiply a number times itself and get a negative 121? The answer is no, right? Because if we multiply two positive numbers together, we get a positive 121. And if we multiply two negative numbers together, we get a positive 121. So there's no way for us to get a negative answer out of multiplying a number times itself. So we say that the square root of negative 121 does not exist. And it turns out that what's happening here is that the square root of negative 121 is not a real number. So in section 8.8, we're going to talk about a different set of numbers that's going to allow you to take the square root of a negative number. But for now, for section 8.1 and 8.2, we cannot multiply two real numbers together to get a negative 121, so this square root does not exist. Okay, let's go to number 3. We've got square root of 225. So that's kind of a big number. And if you cannot see the square root right off the bat, you might want to do a factor tree. Okay, so let's do a factor tree. And we know that 225, that 5 goes into 225 since it ends in a 5 here, right? And 5 goes into 225 45 times. So 5 times 45 is 225, right? And then for 45, we know that 9 goes into 45 9 times 5. And then 9, we know that's 3 times 3. So what we've got here is that 225 is we've got 2 3's, so that's 3 squared, times 2 5's, so that's 5 squared. So we've squared a 3 and we've squared a 5 to get 225. So when we're talking about the square root of 225, that's the square root of a 3 squared times the square root of a 5 squared, square root of 9, which is 3, right? And square root of 25, which is 5. So the square root of 225 is 15. Okay, I also want to show you that you can find this square root in your calculator. So let's go to the calculator for a minute. Okay, so I went to my calculator. I located the square root button, which is right here in my calculator, it's over the x squared button. And then I have to use the blue key to get to it. So I did second x squared and put the square root there and 225. And then I hit enter and I got 15. For problem number 4, we've got the square root of 20. And again, we're going to go ahead and do our factor tree for that. So we've got 20 is 4 times 5. And 4 is 2 times 2. So we do have a square here. We have two 2's, right? And a 5. So what we do is the square root of 20, which is the square root of 2 squared or 4 times the square root of 5. We go ahead and evaluate this square root, this first square root, which is the perfect square. And we get 2 for that, right? Square root of 4 is 2. And then this square root of 5 just tacks on as the part of the square root of 20. So you want to evaluate the perfect squares. Those perfect squares will end up as coefficients. They'll end up in front of the radical expression. And any factors that are not perfect squares stay in the radical sign. All right, so 72, square root of 72, that's another one, right? Because 72 is 9 times 8. 9 is a perfect square, you know that, 3 times 3. And then 8 is 4 times 2, and 4 is a perfect square, that's 2 times 2. So you've got 2 3's here and 2 2's there, and then the extra 2, right? So anytime you have two factors that are the same, like the 2 3's, that's a perfect square. So 1 3, the square root of 3 squared is 3. So you're going to have, okay, let's write this down. We've got these 2 3's, 3 squared. These 2 2's down here are 2 squared, and then this extra 2 is here on its own. So we're going to take the square root of 3 squared, which is 3. So that comes out of the radical. The square root of 2 squared, which is 2, that comes out of the radical, multiplies times the 3. And the extra 2 stays in the radical as is radicand, right? And then you multiply the 3 times 2 together, and you get 6 square root of 2. So square root of 72 is 6 times the square root of 2. Okay, let's go to the next one. And in this next problem, we have 3 times the square root of 98. So we're going to first evaluate the square root of 98, and then we will multiply times 3. Okay, so square root of 98. So here's 98, and 98 is 2 times 49. 49 is a perfect square. It's 7 times 7. So there's our perfect square. We have a single 2, though, left over. So that's going to stay in the radicand. But this perfect square here, the square root of 7 squared, that's going to be 7. So we've got square root of 98, which is the square root of 7 squared, times 2. The square root of 7 squared is 7, and the extra 2 stays in the radical. And now what you're going to do is you're going to take that 7 and multiply it times the original 3. So 3, so you got 3 times 7 square root of 2, which is 21 square root of 2. So that's the square root of 98. No, that's 3 times the square root of 98. Okay, here we have the negative square root of 150. So the opposite of the square root of 150. So we're going to start with the 150. Here's our tree. 15 times 10, right? And then 15 is 3 times 5. And 10 is 5 times 2. So we have 2 5's here. And then we have an extra 3 and an extra 2. Okay, so negative square root of 150. We have negative, it's like a little invisible negative 1 here. I'm going to put a negative 1 there. And then we're going to multiply that times the square root of 5 squared times 3 times 2, right? Because that's what the 150 is. And then the square root of 5 squared is 5. So that gets multiplied times the negative 1, and you get negative 5 square root, and then the 3 times 2 that's left over stays as a radicand 6. So negative 5 square root is 6. So are you starting to get the feel for these? Okay, so now we have 5 plus the square root of 243. So that's different than last time, right? Last time we had a coefficient in front of the radical. We had a negative 1 times, right? Let's look over here, negative 1 times. This time we have an addition. Okay, so that makes it a different thing. So let's go ahead and do our factor tree on 243. So 3 goes in there times 81. 81 is our perfect square, isn't it? It's 9 times 9. 9 times 9. Matter of fact, I'm going to leave it just like that because I know 9 times 9, that's a perfect square. So we have 5 plus, okay, we've got this 243 is 9 squared times an extra 3, right? 2 9's and a 3. So we can take the square root of the 9 squared, that's going to be 9, and then the extra 3 stays in the radical, and this says plus 5. Now be careful here, don't go too far, don't overachieve this. These two terms with the addition in between, they're not like terms. They're not like radicals. So in order to be able to add these two terms together, they would both have to have a radical 3 behind them. They would both have to have a radical 3. So believe it or not, right here, 5 plus 9 root 3, that's done. That's as simple as it gets. Do not overachieve this. Do not try to add these two numbers together. Okay, so that's your final answer. Because in order to add radicals, they have to be like radicals. Not the same with multiplication. Like you saw in number 7, we could multiply the -1 times the 5 and make it a coefficient -5√6. But for addition and subtraction of radicals, they have to be alike. So stop right there. Number 9, we have square root of 112. So 112, let's see, 2 goes in 56 times, right? And let's see, this is what, 8 times 7. 8 times 7. And then 8 is 2 times 4, and 4 is 2 times 2. So we have 1, 2, 3, 4 2's and a 7, right? So we have 2 pairs of 2's, right? So square root of 112 equals, we've got square root of 2 squared times another 2 squared times a 7. So 2 times 2 times root 7, because we have the 2 perfect squares, they come out of the radical. And the 7 stays in. And then we multiply those two as a 4 square root of 7.